Hello everyone, welcome back and let us continue with our discussion with rates of reactions from Unit 4. First, let us try to solve this problem here. The conversion of molecules X to Y follows second order kinetics. If concentration of X is increased to 3 times, how will it affect the rate of formation of Y? Now the reaction is the reactant X being converted into the product Y here. If concentration of X is increased to 3 times, how will the formation of Y be affected? Let us try to see this. Now here, for this reaction, rate is given by K into X raised to power 2 because this is a second order reaction, a second order kinetics. That means the reaction follows second order kinetics. So rate will be equal to K into concentration of the reactant X raised to power 2. This is the rate expression for this reaction. Now if concentration of X is increased by 3 times, that means tripled. If concentration of X is tripled, then what happens to the rate? Rate will be equal to K into X. The concentration of X is tripled, increased 3 times. So this we multiply by 3 now, and since it is still a second order reaction, the power is 2. So rate will be equal to K into X square into 3 square, that is 9. Let us write X like this. Rate was this much, K into X square. After the concentration is tripled or increased by 3 times, the rate becomes this much. So rate was this much, now it is multiplied by 9. That means if the concentration of X is tripled or increased by 3 times, then the rate is increased by 9 times. So the rate becomes 9 times faster. Now, just suppose if this is a first order reaction, not a second order reaction, then what will happen to this rate of the reaction if concentration of X is increased 3 times again? Once again, we have X turning to Y. Rate will be given by K into concentration of X raised to power 1 if it is a first order reaction. So this is the rate of this reaction. If concentration of X is tripled again like before, then the rate becomes K into 3 times of X because concentration of X is increased by 3 times, but the power is 1 only because it is a first order reaction. So rate will be equal to K into X, concentration of X, into 3. This was the rate before. This is what we have multiplied by 3. So if it is a first order reaction and the concentration of the reactant is tripled or increased by 3 times, then the rate also increases by 3 times. The rate also is tripled. Now, molecularity of a reaction. Molecularity of a reaction, it refers to the number of reacting species, which may be atoms, ions, or molecules, that are taking part in an elementary reaction, which must collide simultaneously in order to bring about a chemical reaction. So, molecularity simply means the number of atoms, ions, or molecules that collide together to bring about the chemical reaction. So if only one species is involved. If only one reactant species is involved, molecularity will be 1. That means it will be a unimolecular reaction. But if the reaction involves collision between 2 molecules, then it will be called as a bimolecular reaction, and its molecularity will be 2. Likewise, if 3 molecules are involved, if the reaction involves collision between 3 molecules, then its molecularity will be 3. It will be called as a trimolecular reaction. Now, one thing to remember here is that the probability of more than 3 molecules colliding and reacting simultaneously is very low. So, reactions which involve more than 3 molecules are very rare, and if they take place at all, they take place in a series of steps. Now, reactions that take place in one single step are called as elementary reactions. Those which take place in a series of steps are called as complex reactions. So, reactions which involve 1 or 2 molecules only, they will usually take place in one single step, and they will be called as elementary reactions. But those which involve 3 or more usually take place in a series of steps, and those will be called as complex reactions. Now, in a complex reaction, each single step will be an elementary reaction, and the slowest step among them will give us the rate of the reaction as well as the order and molecularity of the reaction. Now, if we have NH4 NO2 decomposing to give nitrogen and water, ammonium nitride decomposing to give nitrogen and water, this reaction involves only one reacting species. So, molecularity for this will be 1. It will be called as a unimolecular reaction, and this, since it takes place in only one single step, it will be called as an elementary reaction. Likewise, if hydrogen iodide decomposes to form hydrogen gas and iodine, here we have 2 molecules of hydrogen iodide. 2 molecules of hydrogen iodide colliding simultaneously to give rise to the products. So, this will be a bimolecular reaction. Molecularity will be 2. Likewise, if there are 3 molecules involved, it will be a trimolecular reaction, and so on. One thing to remember, order of a reaction can be 0, it can be fractional also. But molecularity of a reaction can never be 0, because if molecularity is 0, it means there are no reacting species, no reacting molecules colliding or giving rise to the products. So, molecularity of a reaction can never be 0. Now, it is not always easy to calculate the instantaneous rate of a reaction. So, if we cannot calculate the instantaneous rate of the reaction, we will not be able to write the rate equation. And if we are not able to write the rate equation, we will not be able to write the order of the reaction or calculate the order of the reaction. So, to avoid this problem, we derive these integrated rate equations, and these equations relate the concentration of the reactants at different temperatures or at different times to the rate constant, that is K. So, let us try to derive these integrated rate equations for first order reactions and zero order reactions. Let us first derive it for a zero order reaction. Let us consider a general reaction in which a reactant R turns into products. According to our definition of rate of a reaction rate is equal to the change in concentration of either the reactants or products. So let us take the change in concentration of the reactant here divided by change in time. If we write the rate equation for this reaction, then rate will be expressed as rate equal to K, the rate constant, into concentration of the reactant R raised to power 0, because this is a zero order reaction. So from these two equations, we can write minus dr by dt equal to K into R raised to power 0. But any term raised to power 0 will be equal to 1. So dr by dt will be equal to K only, because this becomes 1. Rearranging this, we can write dr equal to minus, if we bring it here, minus K dt. Then we integrate this. On integration, we will get integration of dr will give us R, and integration of this will give us Kt plus I, where I is called as the integration constant. Now let me continue here on the side. At time 0, when the time is 0, then this K into T becomes 0. The product of K and T becomes 0, and this concentration of the reactant at a given time will be equal to the initial concentration, because no time has passed. At time 0, the initial and final concentrations will be the same. So at t equal to 0, we can write minus Kt equal to 0, R equal to R naught. Let us take this as equation 1. We apply this in this equation 1. So what happens? What do we get? R becomes R naught, Kt becomes 0, and we have the integration constant I. That means I equal to R naught at time 0. Then we put this value of I in equation 1 again. Let us write putting the value of I in equation 1. Here we have R equal to minus Kt plus I, which is now equal to R naught. Then if we bring Kt here, we will get Kt equal to R naught minus R. This is the general integrated rate equation for a zero order reaction. Now, here we have R equal to minus Kt plus R naught. If we compare this equation with the equation of a straight line, which is y equal to mc plus x, this is y, this is m into c, and then this is x. So if we draw a graph, if we plot this concentration of R against the time, on plotting R against time, we will get a straight line like this, and the slope of this graph will be equal to minus k. So slope will be equal to minus k, and this intercept will be equal to r naught. Again, half-life of a reaction is the time period in which half of the reactant gets used up. So if we start with 10 gram of a reactant, the time period in which the concentration 10 gram becomes 5 gram, that will be the half-life of the reaction. Similarly, if we start a reaction in which A turns into B, initially we take 100 gram of A. The time period in which this 100 gram of A turns to 50 gram, half, that time period will be called as the half-life period for this reaction also. So once again, half-life is the period or the time period in which half of the reactant gets used up, or half of the reaction gets completed. So let us try to derive a relation for the half-life of this zero-order reaction. Here we have the equation Kt equal to R naught minus R. So T will be equal to R naught minus R divided by K. Half-life will be represented by T1 by 2. So for half-life, this we can write as R naught minus R naught divided by 2. Now, why are we dividing this by 2? Because the final concentration will be equal to half of the initial concentration, because half-life is the time in which half of the reactants have been used up. So the final concentration here will be equal to half of this initial concentration. That is why we are writing R naught divided by 2 here. So on simplifying this, half-life will be equal to this much, which will give us R naught divided by 2K. This is the relation that we can use for calculating the half-life period of a zero-order reaction. In the same way, we can calculate the integrated rate equation for a first-order reaction also. So, for a first-order reaction, let us say a reactant R turns into product P. For this first-order reaction, rate, once again, according to our definition, will be change in concentration of the reactant by change in time, and according to the rate equation, rate will be equal to the rate constant K into concentration of R raised to power 1. In this case, concentration of R will be raised to power 1 because this is a first order reaction. Now that is all the time we have for today, so we will continue with this derivation in the next class. Thank you.